Good afternoon, everybody. Today we're going to talk about how we can leverage monoids, a topic from mathematics, and we can deliver the image gesture controls that our users are expecting on mobile applications. So first, a little bit about me. My background is actually in mathematics. I have a mathematics degree, and I've done research in knot and graph theory. These topics were actually the first time in my research where I discovered monoids. And it wasn't the first time. Every time I did a new research project, the monoids keep coming up. And programming was not an exception, so that leads us to today's talk. So our topics, we're going to start with what is monoids, and specifically group theory, the field that monoids come from. And then we're going to talk about how we can represent monoids in Typescript. And then from there, we're going to talk about translating on pan or dragging with your finger, zooming on pinch, and sorry, the last one is just the double tap. We're just going to talk about resetting double tap. Sorry, I think I pulled up the wrong slides. Okay, picking up where we left off. So last thing, we're going to talk about resetting on double tap. So what is group theory? Group theory studies the algebraic structures known as groups, and they're central to these broader fields of abstract algebra and category theory. Today, we're not going to talk about groups, rings, or fields. We're going to focus on monoids. So I'm going to start with the definition of a set, build with the definition of a magma, build to the definition of semigroup, and then build to the definition of a monoid. So starting with the basic building block of monoids is a set. In mathematics, a set is a finite or infinite collection of elements in which order has no significance and no element can be repeated in that set. A good example would be our integers, our negative whole numbers 0 and our positive whole numbers. So a non-example would be if I had the set 1 and 1. So building to a magma is if we pair that set with a binary operator with closure. So the binary operator just means that we're going to take two things that's going to combine to be one thing, and closure means that the result of that operation is still within our set. So keeping with our integers under addition is a good example. If I add any integer with any other integer, I will get an integer back. So as a non-example, what if we just take our positive integers, known as our natural numbers, still with a subtraction? This is not closed. I can take 1 and subtract 1 from that and I get 0, and I'm outside of my set now. I don't have closure. Building to a semigroup. A semigroup is a magma, but that binary operator is associative. The associative property means that I can combine from the left to the right or from the right to the left. So our integers, taking 1, 2, and 3, if I want to combine them, I can combine the 2 and the 3 to get 5, plus the 1 to get 6, and it doesn't matter if I wanted to combine the 1 and 2 to get 3 first and then add the last 3. But this property is not definitive. This property cannot be assumed to be true for all sets in a binary operator. So a fun non-example would be if I take the classic rock, paper, scissors. If I try to combine rock, paper, and scissors, if I do it left to right, we have rock against paper, where paper wins, and now it's up against scissors, where scissors win. So combining it left to right, I get scissors. Taking the same elements in the same order, but we're going to combine them right to left. Scissors against paper gives us scissors, and now scissors is up against rock, where rock wins. So this is an example that is non-associative. We cannot assume that combining it left to right is the same as right to left. Finally, to the point of the talk, a monoid. A monoid extends a semigroup with the existence of an identity element. This identity element is something that I can apply to the left or to the right of any element in my set, and I get that element back. So my integers under addition, 0 would be my identity element. I can add 0 on either side of 2 and still get 2 back. A non-example is if we restrict that to just our natural numbers under addition. We no longer have 0, we no longer have a an identity element. So as a quick recap, we have magmas that have a binary operation that is closed. The semigroup is closed, but that operation is also associative. And then a monoid has the binary operation that is closed, it's associative, and it has this identity element. So now we understand what it means in mathematics, but how can we actually translate that into TypeScript? So how can we represent these math concepts in programming? We're going to extend, instead of thinking of a set as like a finite or infinite set of things, we're going to think about that as a type. So my type number just represents all real numbers, and my type string would represent any combination of characters. And thinking about sets as types leads us directly into a binary operation. So here we just need a binary function, and closure is really easy to define in TypeScript. We're going to take a generic type T, and we're going to have a function that takes an A and a B, both type T, and that function is going to return one thing, same type T. So here we have closure because we're taking two things of the same type, returning that same type back. So closed binary operator is not something that we would say often. Something that we're more familiar with is the concat function. We're very familiar with concating strings, taking two strings, making one. But here we're going to think about it more generically. T can be anything, and we're going to see that that concat function can mean different things depending on the type. It could be merging, any type of putting two things together to return one thing. So for a magma, remember we just need that concat function and it just needs to be closed. So we're going to have an interface on a magma with a generic type T. It's going to be an object with a method called concat, and that concat method is going to take two things, return one thing, all of type T. So an example, at the top we have the interface for a magma, and then let's use that interface. So how about a magma remainder? The remainder operator, how it works is it tries to take two numbers, tries to take the second number and put it in as many times as it can into the first number, and what the remainder is what it returns. So our concat function is going to take an A and a B. It's going to use the percent sign, the remainder operator, and do A remainder operator B. So if I do magma remainder dot concat and I give it 5 and 3, it's going to return 2 because 3 goes into the 5 one time with a remainder of 2. And this is a good example of a magma because this operation is not associative. If I gave it 3 and 5, I would not get 2. So our semigroup interface is going to look identical to our magma interface because the semigroup only differs from a magma by a property, and that property is not something that we can ensure or test for in TypeScript. It's actually the responsibility of the programmer to know, oh, this operation is associative, therefore I need to use the semigroup interface. So let's see an example. So we have our interface. It's going to be an object with the concat method, takes two things of type T, returns that one thing of the same type. We're going to define it on numbers with addition. So our semigroup type is going to be number. It's going to have a concat method. It's going to take two things, an A and a B, and just add A and B. But maybe we want to do more complex things. That's kind of a simple example. So what if we have a type that's a pair that has an X and a Y property, and you can kind of think about that as like a coordinate on a coordinate system. We can use our semigroup sum to extend to a more complex semigroup. So here we have a semigroup pair sum. Its concat function is going to take two pairs, a P1 and a P2. And then it's going to return another pair that has an X property. And to get that X property, we want to add the X's from P1 and the X from P2. So let's use our semigroup sum concat function to do that. So semigroup sum.concat P1.x, comma P2x, and then we'll do the same thing for Y. So a monoid only differs from a semigroup by an element, the identity element. And here we're going to call that element empty. So it's going to extend semigroup and give it this read-only property called empty. And the relationship that we have here is that the concat function, if it gets any number x with the empty, it will return x, same within the reverse order. So an example would be a monoid sum. So on line 10, we're defining a monoid sum. It's a monoid on numbers. Our concat method is going to take two numbers, an A and a B, and add those together. And that looks identical to our semi-group that we just defined, but it's going to have an added property. It's going to have the added property empty. And here it's 0 because when we're in addition, 0 is our identity element. And we're going to extend that to a pair again. So our monoid pair sum, you can see that the concat function is identical to our semi-group, and we've only added a new empty property. So we can even reuse our empty property from the monoid sum. So the x property is just monoid sum empty, and the y property is just monoid sum empty, and that just means x is 0, y is 0, it's the origin. So we've gone over what group theory is, how to implement it in TypeScript, and we're finally ready to translate on pan. So first, what is a pan? A pan is when you put down your finger and then immediately start moving, and pans are executed slowly and allow precision. So there are other touch events that we could attach to, like a touch event or something that would get some information, but the pan is special because it's for precision. That's what we want to be able to move around the image. So I wrote this in NativeScript, but we can think about this a little bit generically. So I might have an on pan, and it'll get pan gesture event data, and it's going to get a delta x, a delta y, and a state. Delta x represents how far the user has moved their fingers since putting it down in the x direction, and then delta y is that same thing but in the y direction. And then the state's going to represent how far we are in the pan. Have we just started, are we during it, or are we at the very end? So here's an animation over time. So we can see that when the user first puts down their finger, they haven't moved, so our delta x is 0, our delta y is 0, and our state is 1, meaning they have just started. Next, they've moved 1 in the x direction, 0.667 in the y direction, and our state is 2, that means they are still moving. Next line is a continuation of that movement, and then the next one is their ending position. They're at 3, 2 now. They've moved 3 to the right of where they started, 2 up from where they started, and our state's 3. They've lifted their finger. We're now done with the pan. So how can we use this event data to implement a translate on pan feature? We're going to do it in 2 steps. We're going to continuously combine the delta from the event with our last known stopped position. And spoiler here, we're going to use a pair sum monoid that we saw. And then step 2, to make this actually continuous, we have information that we need to keep reading from. When the user stops, we need to save that stopped position so that we can continue this process. The user can put down their finger, move it, lift it up, put it down, and keep moving it around. So we're going to use the Monoid Sum that we used earlier. Our Concat Function is just going to take 2 numbers, add them together. Our empty is going to be 0. Remember that our type is a pair, an x and a y, and this is the same monoid pair sum that we saw earlier. So we're going to keep track of 2 variables. We're going to keep track of where the picture is currently. We're going to call that the current position. And then we're going to keep track of where the user last stopped, and that's going to be our last stopped position. We're going to initialize both of those using our monoid pair sum empty. It's very convenient. And that's just going to mean x is 0 and y is 0. So then in the on pan, we're going to get that on pan gestured data, delta x, delta y in the state. We're going to start by combining the 2 deltas into 1 delta. So we're going to say const delta and give the x the delta x and the y the delta y. And then here is where we are continuously combining the stopped position with the delta. We're going to reassign current position to the monoid pair sum.concat stopped position and delta. We're going to continuously combine that stopped position with the delta that we're getting in from the event. And then finally, if the state's 3, that means the user has stopped, we need to save that stopped position so that we can reiterate this process. So what if we put a console log here? What would that look like? You can see the state starts at 1. Our last stopped position was origin. The user hasn't moved the image yet, so it's at 0, 0. And we're continuously getting these deltas in. So on the first line, our delta is 0, 0 because the user hasn't moved yet. But then on the next line, you can see that the user has moved and we're getting those deltas. And then our current position is the stopped position combined with the delta. And see here that the user has stopped at 3, 2. So what if they wanted to continue at 3, 2? What would that look like? So this is a new event that's starting. The state's 1, they just put down their finger. We're starting at 3, 2 this time, and we can start at the starting position. Delta is 0, 0, and so our current position is still 3, 2. Then on the next line, you can see that they're moving 1 to the left. The next line, they're moving one more to the left, and then the next line, they're moving 1 more to the left. They're ending at 0, 2. So that's how you implement the translate on pan. You just use the monoid pair sum, continuously combine those deltas with the last known stopped position. Easy. Next, we're going to do zoom on pinch, so how to enable the pinch zoom. So our on pinch is going to get pinch gesture data. It's going to get a pinch scale and a state. So what exactly is the pinch scale? Let's console log that out and inspect it. Okay, so it started at 1 when the user put down their finger, and then it started to increase as their fingers got further apart. So that means that our user is trying to zoom in. And you can see here that the state is following the same model that we've represented before. 1 starting, 2 we're in the middle of it, 3 we're done. Okay, here the user is putting their fingers and they're moving them in. You can see that the pinch scale still starts at 1, but the pinch scale gets smaller. So how are we going to use this event data to implement the zoom on pinch feature? We're going to do it in 4 steps. First one is we're going to determine if the user is pinching in or out by comparing the last pinch scale that we got with the one that's coming in currently. And then the second is we're going to use a product monoid to scale the image up or down. And all that means is that we're going to multiply it by something bigger than 1 to make the image bigger. We're going to multiply it by something smaller than 1 to make it smaller. And then 3, we're going to do something for our users. We're going to restrict the user from zooming too far in or out. We don't want our users making it too big or too small. And then 4, to make this a continuous loop, we've got to save the previous pinch scale so that we can compare it when we repeat the process. So we're going to use the monoid product. The concat function is going to take 2 numbers. It's going to multiply those numbers together. Our empty here is 1 because that's the number that you can multiply anything by and get that number back. We're going to have 3 helper functions to help us do this. The first one is going to help us determine if the user is pinching in or out. We're going to use a compare function. So this compare function is going to take 2 numbers, and it's going to let us know if A is less than B, A is B, or A is greater than B, and it's going to represent that in 3 states, a -1, a 0, or a 1. So if A is B, they're equal, it's going to return a 0. If A is greater than B, it's going to return a 1, and if A is less than B, it's going to return a -1. The second step is we need to use the product monoid to scale that image up or down. And so 1, it needs to know whether we're going in or out. So it's going to get an order. It's going to get something returned from the compare function to know if we're going in or out. And then it's going to get the current image scale to the thing we actually need to multiply to make it bigger or smaller. So if the order is 0, the user hasn't pinched in or out, we're just going to return the same image scale back. But if the order is -1, that means that the user is pinching in, meaning they're trying to zoom out. We're going to use the monoid product concat function to do image scale times a 0.975. Otherwise, they're trying to zoom in, and we're going to multiply by something bigger than 1, say 1.025. The 0.975 and the 1.025 are arbitrary. Any number bigger than 1 could have worked, any number smaller than 1 could have worked, and it's kind of figuring out what is best in the feeling. The last helper function we're going to use is a clamp function, and that's going to help us restrict the users from zooming too far in or out. It's going to take a number that we want to clamp, we want to bound it, and then it's going to take what the minimum it can be and what the maximum it can be, and then return a number in between the min and the max. To do that, we can use our compare function. So if A is less than the minimum, we need to return the minimum. If A is greater than the maximum, we're going to want to return the maximum. And then otherwise, we know that A is between the min and the max, so just return A. So we're going to keep track of 2 variables, the image scale and the previous pinch scale. We're going to initialize both of them with the monoid product empty, just 1. And then in our on pinch, we're going to get that pinch scale, and we're also going to get the state. So we're going to start by getting the order. We're going to decide whether the user is zooming in or out by using our compare function. So we're going to compare our pinch scale that we're getting in with our previous pinch scale that we're going to be saving. And then the next line, we're going to get a candidate for the scale. We're going to use our calc scale to do that. And we're going to give it the order, whether they're zooming in or out, give it the image scale that it needs to scale up or down. And then the next line on line 7, there's a typo here. The const shouldn't be there because we're reassigning image scale. So here, image scale is going to be equal to we're going to clamp the image scale candidate. It's just a candidate because we don't know whether or not we want to keep it. Because we want the image scale to stay between like 1 and 5. We don't want the user making it smaller than 100%, and maybe 500% should be the maximum. And then on line 9 is our step where we're saving the previous pinch scale each time. So if the event is done, meaning the event is 3, let's reinitialize the pinch scale with our monoid product empty. Otherwise, we're continuously going. We need to save the pinch scale that we got from this event as the previous pinch scale. So again, let's insert a console log and inspect it. So here, we are zooming out. Our pinch scale is getting bigger, and we can see our image scale is also getting bigger. Now we're zooming in, our pinch scale is getting smaller, and our image scale is also getting smaller. So we've now implemented zoom on pinch. We need to implement our last thing to help our users is a reset on double tap. The user has moved the image all over the screen and now they don't like their changes and they need it back to reset. This is pretty easy because we've set up our monoids. All we need to do is reinitialize all the variables that we've been keeping track of. So to reset the position, all we need to do is current position and equal the monoid pair sum empty. Remember, that's just 0, 0. The last stopped position we'll reinitialize as the same thing, 0, 0. And then to reset the scale, we'll do the same thing. Current scale, but this is our monoid product, that's the 1. And then our previous pinch scale with 1. So the conclusion of this talk, I hope, we've kind of gone through the exact ways of how to implement it, but I hope what you've taken away is that monoids are very simple, but they're amazingly powerful concepts. When we're using this language in programming, we give so much more information to other readers of our code. Using a magma might seem like an overcomplication, but that helps people who are using it use it correctly. They know what properties it has. They know when they can and cannot switch the numbers around and things like that. It keeps us from making mistakes in our code. And then 2, we can leverage group theory to deliver the features that our users want. We can use mathematics in programming. To do this in TypeScript, I recommend a library called FPTS. It has a lot of built-in, it has the magma and the semigroup and the monoid types all built in already. And it has even an article getting started with FPTS, and it kind of covers a lot of the things that I've covered and more. And then you can go even deeper into the group theory and programming. So a near surface exploration would be the podcast that I can recommend, How Abstract Algebra Solved Data Engineering. And this is a story of how Twitter engineers came up with a unique solution to data engineering. And then if you really want to deep dive, there's a great book. Sorry, it's 498 pages, but it comes accompanied with a video playlist that you can watch also. Is there time for questions? Okay. Are there any questions? Oh, yeah. This one? Uh-huh. This is a great library. A great library.
Do you have a library of Typescript functions with some of the monoids that people use?
Yeah, this is that. Mm-hmm. Any other questions? Yes?
Where can we find the slide deck?
That's a good question that I'm not sure. I did provide it to the conference. The conference should be providing it to everyone. Mhm. You can find me on GitHub and LinkedIn. On GitHub, I'm Zerfet. I've used the library in all of my projects, so you can see the library actually being used in a project. And thank you, everybody.